Hello everyone. In this video, we are going to look at a new topics. We're going to look at deterministic context-free grammars. In particular, we are going to spend some time explaining the concepts of LRK grammars, which is so for a fixed K, LRK grammar is equivalent to a deterministic context-free grammar. And it has important applications, for instance, in designing compilers. Okay, so when we look at regular languages, we know that deterministic finite automata are equivalent to non-deterministic finite automata. So that implies that for regular languages, we don't have deterministic regular languages or non-deterministic regular languages because they are the same. So which means that we don't have to talk about, when we mention regular languages, there is no difference between deterministic or there is no difference between deterministic and non-deterministic. However, for context-free grammars, there is a difference. Okay, so that's the topic we are going to talk about today. Okay, so first we start from deterministic PDA. Okay, as we know that context-free languages could be represented by PDA. It can also be represented by context-free grammar. So we can, when we study deterministic context-free languages, we could approach this from deterministic PDA or from deterministic context-free grammars. So we first look at deterministic PDA. So a deterministic PDA is a six-tuple, Q, sigma, gamma, delta, Q0, and F. So these components are the same as PDA, except that the delta function, the transition function delta, now is in a deterministic form. So that means that at the right-hand side, okay, so remember when we look at PDA at the right-hand side, it is a power set, okay, 2 to the Q cross gamma epsilon. So that is a power set. In deterministic, so in deterministic PDA, we would only have one next move, okay, instead of a set of next moves. So this is one. So that is there's one difference. And also, if you look at the right-hand side here, okay, so this is a sigma epsilon and gamma epsilon. It means that you could take a symbol, an input symbol as input, or you take epsilon as input for the middle part. You could also take a stack symbol as input or epsilon as input, right? So that means you have two choices here, two choices here. All together, you have four choices on the left-hand side. For deterministic PDA, we emphasize that among these four choices, exactly one choice will not go to this dummy node, this empty set. So we think of this empty set as a dummy. So there is only one, exactly one, okay, that will go to one of these, okay? The other three will go to this dummy node, and the dummy, of course, doesn't go doesn't go out. So that is like a sink. You just go there, right? So that is deterministic PDA from the definition. Okay, so now let's look at a concept called reduction, and from that we also talk about a very important concept called handles. So remember, when we look at context-free grammas, we have, in order to talk about what it means by generating a terminal sentence or terminal string from this grammar, we introduce the concept of derivation, okay? So maybe I should start a screen and talk about this. Okay, so we have, so let's say we have a context-free grammar CFG, and of course we know that it has a set of variables. This is a finite set of terminals, also finite, and you have a set of rules, context-free grammar rules, and you have a start variable. Okay, and then for any string, well, basically what we are interested in here is that when we say a symbol can derive a string x, okay, this x could be could contain variables and terminals. So when we say A derives this, it really means that I have, we first define one step derivation. So this from here, it just means that I have a, so let me remove this A. Let's say, things U, okay, go to V. This is a multiple step. So this is one step. It really means this, that U, so this really means that U contain a variable. Let's say we have X, Y here. It contains a variable. And then A, let's say going to Z, is a grammar rule. Then we can replace A with Z. So we get V, X, Z, Y. So this is a one-step application of one rule. So then we will say that this U derives V in one step. So, and then if you have, so this means that you have intermediate. You have intermediate strings, and eventually that's V, right? So that's what the star means. So this is a derivation. So derivation is like a forward so derivation is a forward direction, which means that you look for variables, okay, and then look for grammar rules such that at the left-hand side, you have the variables appear in your string. And then, so that is a forward direction. So now, so this is forward direction. But this is not really parsing. Now, for parsing, you are really given a sentence. Let's say you are given a sentence S, right? So which is a terminal string S. What I want is I want to go backward. So I want to go backward. And trying to find whether, let's say, maybe we can say S is like this, X, maybe H, Y. And then I want to see whether there is a rule, grammar rule, T arrow H, such that I can go backward and replace H with T. So then I'm going to say, so let me go to the next screen. So we have, let's say S. So I have a string H. So all these X, H, Y are strings. Okay, and also I also have a grammar rule like this. And then I can say, let me say this ST Y, of course, derives SHY. But since I go backward, I start from here. So I'm going to say XHY is reducible to XTY. Okay, so that is different direction. So then we want to use a symbol, a notation. So this is reducible is, in our textbook, we are using this tail arrow. Now this arrow has a tail. So then we can say SHY going to STY. And this H then is called a handle. Okay, so this is called a handle. Okay. So what we really want to in parsing is we want to find, okay, let's say it goes to U1, and then U1 goes to U2. Okay, keep on doing. Finally, maybe you go to UK. It's a U, not mu. And that actually is a star symbol. So then you, from a sentence, you find a handle each step, and then you end up at a star symbol. Then, of course, now I parse this string small s. So this is a capital S. So this is a capital S and small s. Okay, small s. So then I'm going to say, right, parsing is successful. I'm going to compress this intermediate steps, and we're using a start and put it up here. That means there are several steps involved. So this is just looking at derivation from from the reverse order, and we call that reduction. Okay, so now let's look at this slide. Sorry. Okay, so let's go over these two concepts of reductions and handles. So again, let G be a context-free grammar, and we write U tail arrow V if V derives U, right? So this is the reverse order. And we also write U tail arrow V with a star sign if V derives U, again with the star sign, which means that it involves multiple steps. And then we call this U tail arrow V with a star sign, U a reduction. So in other words, U is reducible to V. Our goal in parsing is to reduce a terminal string U to the start variable S. And then we call this a reduction from U. So each time the reason we call it reduction is because each time we reduce the length of the string, well, more or less, right? Because you use to shorten the current string. Okay, so each time we reduce the length until we reduce to one variable, which is S. All right, so that's called reduction from U. And then we look at, again, the concept of handle. So let U be XHY. Again, XHY, each of these are strings. And V be XTY, and T arrow H is a grammar rule. Then we say that H is a handle of U. H, of course, is a reducing string, but we normally call it a handle. And of course, when you mention a handle, it also means that there is such a rule, right? T arrow H is a grammar rule. Otherwise, you don't have otherwise that H is not a handle. So only when this is true, then H is a handle. So when there is no confusion, then we simply say H is a handle without mentioning specifically what that rule is, what that grammar rule is. All right, so that's the concept of handle. And then we're going to say a string is valid if this string is in the leftmost reduction of a string in L of G. Okay, so what that means here is that, let's say I have a string. So let's say I start from U, and then we go to U1. Let's say when we go to U1 here, let's say U may have more than one handle. We always choose the leftmost handle to do reduction. Then that's called leftmost reduction. And then it may involve several steps until you go to your destination. Or let's say this is S. Okay, so this is a leftmost reduction. Then any of these things in between, like so U is valid, U1 is valid, right? Any UI is valid. So that's what this valid string means. Okay, so if a valid string has multiple handles, then G is ambiguous. So what that means here is that even you always choose a leftmost reduction, but for this leftmost reduction, you may have more than one option. you may have more than one ways to choose a grammar rule. So in that case, it is ambiguous. In the next slide, we are going to see an example. Okay, so so now we come down to the last concept. We say that a handle H of a valid string XHY is a forced handle. Okay, it's a forced handle. If it is a unique handle for every valid string XHZ with Z. So what that means here is that, let's say I have a handle HY, and we can write this HY1. We can write this up. Okay, then for any valid string SHZ, we can write this as SHZ1, Z2 up to ZM, right? So this is also valid. And what we are saying here is that if H is a forced handle, then your HZ1 cannot be a handle. And your HZ2 cannot be a handle, and so on. So you cannot, so in other words, the handle is only one. So that really said, so this is really a concept to fortify this, to get rid of this ambiguity. Okay, so to get rid of the ambiguity. So this handle is unique. So the next symbol with H cannot be a handle, which means that you only have a unique handle to apply. Okay, using leftmost reduction. Okay. Okay, so now let's look at an example of a deterministic CFG. I'm sorry, let's first look at an example of an ambiguous reduction, and then we'll define deterministic CFG. We call it Dcfg. So here's an example. So you are given a context-free grammar. So this R here is a star symbol, star variable. So this is a start variable. Okay, so this I would have used S for star variable, but this example is directly copied from the textbook. So this R is a star variable. And then from R, this is the first rule, you go to S or T. Okay, from S, you go to ASB or AB. From T, you can go to ATBB or ABB. And then this context-free grammar accepts this language B union C, where B is a set of strings in the form of M copies of A followed by M copies of B. So it's identical copies. I'm sorry, the length is the same. So M is identical. And C is a set of strings in the form of M copies of A followed by 2 M copies of B. Okay, so now let's see why it is ambiguous. So we're going to look at AA, AB, okay, AAA, BBB. So it is in the language. Now we first look at the first handle, because now you could have more than one handle here. For instance, we could have, so this is A, B, and A, B, B is also a handle, and also is a leftmost handle. So you have two choices for selecting a leftmost handle. Okay, so if you choose AB, then you get down to ASB, because AB comes from S. So you replace AB with S, you get down to this. Then from here, you can see here, you only have one handle. It's leftmost handle and also is unique. Okay, so the next one is that you choose ABB instead of AB, right? And so that explains that this is ambiguous grammar. So now we are going to get rid of this ambiguity and define deterministic context-free grammar. So this is the definition here. Okay, a CFG is deterministic if every valid string has a forced handle. So this is a valid string, but its handle is not forced because you have two choices. So ABB, and so this AB is a handle, but ABB is another handle. Okay, so that is not forced. So we get rid of this, then we call it deterministic context-free grammar. Shorthand for that is DCF. DCFG, okay? And the language generated by a DCFG is DCFL, okay? So then we can, so this is the result that says that DCFG is a proper subset of DCFL is a proper subset of CFL. Okay, so this is different from regular languages. As we said earlier, for regular languages, there is no such difference. Okay, so now let's move on to the next slide. We are going to look at parsing and this grammar LRK. Okay, so this LRK is a shorthand for a pretty long name that we're going to mention later. Okay, so DCFG, so deterministic context-free grammars, are of major practical importance on efficient parsing. But the requirement that all handles are forced is often an obstacle in designing a DCFG. So instead, we are going to look at something that offers the best of both worlds. So which is easier to work with, and it guarantees deterministic CFGs. So that's called LR of K. So these grammars are close enough to DCFGs, and as a matter of fact, they could be converted. Okay, they are equivalent to DCFGs. Okay, so this is a direct conversion. They can be converted into deterministic PDAs, and they are expressive enough for many applications. And in this particular LRK, there is a concept called look ahead. Okay, so remember in the previous when we explained the concept of forced handle, we use this example. So we have, let's say H is a handle, and Y, right? So we look for this, we look at this string, and then we can write it as S. I don't know why. There's a zoom, give me this. Okay. When we look at S, H, Y1, Y2, YK. By look ahead, it really means that I can, so I look for, maybe I can look for Y1 and see whether HY1, and then remember at that time we're saying that it cannot form another handle. We can also look for, so hy2, and so on. But in this LR of k, what we are saying here is that, let's say I have another string. Oops. For any string z, let's say as h, so this is y1, so we got z1, z2, cm. So by look ahead of k symbols, that means that, let's say k is equal to 2, then we are assuming this z will have the same, so y1 and y2 is the same as z1 and z2. So by looking ahead a few more symbols, okay. So that's what it means. All right. Okay, so so algorithms for LR of k grammars introduce a new concept of look ahead. In an LR of k grammar, a handle may depend on symbols that follow the handle, right? So that's what we said earlier, but only on the first k of these symbols. And then this LR of k stands for a long name, as we mentioned earlier, which is left to right input processing, rightmost derivations, and k symbols of look ahead. So I should put a quote back here. So this left R and K. Okay, so this is a LR of K look ahead. So now finally we are we're going to mention that this important result that LR of K for any K is equivalent to Dcfgs. Remember, when K is equal to 0, it is just the definition of Dcfgs. So this is a definition, but then when K is greater than 0, it is still equivalent to Dcfg. So that's what this result says. Or can be converted to Dcfgs. Okay, now let H be a handle of a valid string. We say that H is forced by look ahead K if H is the unique handle of every valid string XHZ for Z, where Y and Z agree on their first K symbols, right? So that's on the surface, it looks like an extended notion of forced handles because you look ahead K symbols. Even you look ahead K symbols, they are still unique. So if either string is shorter than K, of course, then the string must agree up to the length of the shorter one. And then now we define what a LR of K grammar is. It is a context-free grammar such that the handle of every valid string is forced by look ahead K. Then it is equivalent to DCFGs. This proof when K is greater than 0, LR of K can be converted to DCFG is an algorithm, but that algorithm is quite involved. Actually, it is converted to a deterministic PDA. Okay, so that conversion is quite involved, and we are not going to talk about that conversion here. If you are interested in it, your textbook, version 3, okay, edition 3, right? Your textbook edition 3 has that construction. If we are using the textbook edition 2, and you don't have that conversion algorithm, okay. All right, so that is the end of this video.